Now we are going to be looking at low intensity and high duration exercise. Submaximal exercise involves the athlete working at a lower intensity over a longer duration to sustain their performance. Because the energy is needed over a longer duration, the athlete would require fats as the energy source, so they can be broken down continuously over the duration to be able to provide the energy needed to produce ATP continuously. An example of this is a marathon runner or a 3,000 metre runner. This is because their sports are mainly endurance, so they have a higher resistance to fatigue than, say, athletes like sprinters who are working anaerobically, as they are using oxygen in order to produce ATP to prolong their performance. They would use at the start of the race their ATP-PC system due to the stored ATP being already in the muscles, and then after the first 2 minutes then they would switch to using the glycolysis system as their dominant system. But as a limitation of this, it produces hydrogen ions and lactic acid. So what the athlete aims to do is to achieve steady state by matching the oxygen consumption with the demands of the exercise, so then they can use the aerobic system. A limitation of the aerobic system is that it is much more complex than the other two systems, and it takes time in order to become dominant. The glycogen that has been broken down into glucose and pyruvate can then be converted into acetyl coenzyme A, which can then be used in the Krebs cycle to release carbon dioxide, and then into the electron transport chain. So then this process can occur. Athletes are mainly mesomorphs because they are made up of a mixture of fast glycolytic fibres and slow oxidative muscle fibres, but in certain sports particular athletes require mainly one type in order to generate the force needed over the duration and intensity. Athletes that partake in low intensity but a long duration would have a somata type of an endomorph with more slow oxidative muscle fibres. This is because these fibres have a higher resistance to fatigue and therefore can continue to contract over a long period of time. But another reason is that the long distance runners need to produce maximum force to propel the athlete forward and maintain momentum. So by the muscles being smaller and having smaller motor units and having a lower body mass makes this easier. This is because if the athlete had the build of a weightlifter, they would find the excess body fat hard to carry, and therefore that would impact the performance, because this would generate power but not enough to be released over a long period of time. So by the athlete having a lower muscle mass means they are more able to produce power over a longer period of time and then sustain this over the continuous period. Another technique endurance athletes use is the idea of running economy, and this is also relevant to a triathlon, shown by the slide, which is how much oxygen is consumed by each stride that the athlete takes. This is why athletes will have adapted to a specific training program where they use techniques which will help them with this. The technique will involve the athlete taking smaller strides in order to use less oxygen to save fuel for periods in the race, like at the end, where they have to change their intensity to sprint to the finish line, or in the example of a triathlon, in the transition periods between finishing the swim to getting on the bike. If the athlete has a technique where they use longer strides which forces the body to move more vertically, it will result in more oxygen being used, as the action involves the muscles to contract more forcefully, which will cause the performer to eventually fatigue, because the rate at which they are carrying oxygen is not meeting the demand, so therefore they have to produce energy anaerobically. This is why the athletes take smaller strides and propel themselves forwards more horizontally to reduce the oxygen used, so they can save it for later and periods where more may be needed. The athletes also use sports drinks and glucose gel, as we previously mentioned, known as glucose ingestion, which is a strategy used to replace the PC stores, and it helps to it contains glucose, which is broken down to provide ATP before or during the race in order to help provide extra energy quickly and prevent the blood glucose levels depleting, which we will come to later. As the intensity increases, the glycogen stores deplete quickly, so if we use these methods we can increase the glycogen stores so we can continue to work at the increased intensity over a longer period of time without fatiguing. It's also important that we maintain these stores because carbohydrates are the main fuel we are using, and this allows us to generate energy quickly as they are hydrolyzed rapidly. So we need to maintain these stores to prevent us from having to burn fats, as although these provide lots of energy, it occurs more slowly, so therefore with the depleted glycogen stores the athlete is forced to slow down as they can no longer sustain the pace before. This slide is showing the different energy sources which are involved in the different intensities. We previously mentioned about carbohydrates and fats and how the long distance runners would benefit more from having carbohydrates to generate the energy quickly, but fats are also useful because they generate energy over a longer period of time, but it means the athlete has to work at a lower intensity. We can see from the image on the left that represents the approximate energy sources for different sport activities, that for low intensity but high duration is represented by the mini triathlon, which consisted of 2 hours, and that 10% of the energy came from proteins, around 45% came from carbohydrates, and around 47% came from fats. From this we can understand that this athlete is using a mixture of fats and carbohydrates during the exercise, because carbohydrates provide us with the most energy and are broken down quickly in order to produce ATP. Therefore the athlete can use this for the duration, but the fats are broken down because they are released over time, so it can provide the athlete with energy over time. From this we can suggest that this athlete would have an RER of around 0.85, as they are using a mixture of both fats and carbs. If we compare this to a 200-metre sprinter, we can see that around 80% of their energy sources are from carbohydrates and around 10% from fats. This is because these events need to generate a large amount of force quickly, and carbohydrates can achieve this, and this is why the athletes would want to preserve these stores, because if they are forced to burn fats, they will not be able to sustain the same intensity and be forced to slow down, which is not ideal in a 200-metre sprint. The graph on the right further shows this and the idea that in lower intensities we have around 20% carbs and 85% fats, and then as the intensity increases to moderate exercise the components are at an equal 50% percentage, showing that the athlete is using a mixture. But then as we transition into high intensity, the carbohydrate percentage increases to 85% and the fats to around 0 when the athlete is working at 100%. So we can see that it changes depending, the energy source changes depending on the intensity of exercise. So we tend to use more carbohydrates in the high intensity exercise and more fats in the lower intensity exercise. This slide is showing the glycogen depletion and how that varies in exercise intensity. So the graph on the left shows glycogen depletion, and this is the idea that as intensity increases, the glycogen stores are depleted faster. This is because the athlete is having to produce more force at a faster rate. In high duration, low intensity exercise, the athlete can exercise for longer periods of time without their glycogen stores depleting, while in more strenuous exercise, the glycogen stores deplete from around 100% to almost none in just under 60 minutes, compared to the light exercise where the stores remain slightly under 100% after 2 hours of exercise because the stores are being replaced. And they're not being depleted because the athlete is meeting the demands of exercise. And working with oxygen helps to break down and replenish the stores without the accumulation of waste products, lactic acid and hydrogen ions, which will then induce fatigue. So it means they have a much greater resistance in longer duration activities than those in high intensity. The bar graph on the right shows the glycogen stores at the start of exercise and the end, and how this varies over 4 days. We can observe that as the days increase, the glycogen stores are depleting each day before exercise and rapidly after. This is because not enough recovery time is being allocated in order to replenish these stores, so therefore the stores are not being replaced, and therefore the athlete can't produce the same force, and so each day their performance deteriorates. We can see that at the start of training the stores seem to deplete quite constantly each day, and at the end of training we can see that the stores rapidly start to decrease because they're being used in exercise. So this is why recovery is really important to an athlete, to allow them to replenish their stores, so this then allows them to work maximally again. And now we're going to look at the strategy of carbo loading. So carbo loading is a strategy mainly used by endurance athletes in order to try to preserve their glycogen stores so they don't deplete as quickly, and so they can be stored and used more efficiently. The athlete consumes less carbs prior to the event and exercises more in order to deplete the glycogen stores. As we can see on the graph that the levels go from 90 to around 20 because they're being used in exercise and not being replaced. This helps to decrease the stores and help with storing. So from day 1 to 3, the glycogen stores are being depleted, and therefore the body thinks that the glycogen stores, there's a problem with them. So when it next has access to a form of glycogen, it will store more and hold on to it more than usual. As we can see from day 5, the glycogen stores have been replenished to even more than before, to now around 120. And in the increase in the days leading up to the event. So in the few days leading up, when more carbohydrates are stored, these are then replenished. The glycogen stores then are increased. As we can see from the graph, on day 5 it was 120, to day 6 around 130, and day 7 around 150. And this will help the athlete to release these and hold on to them more in exercise to preserve the stores so they can resist the effects of fatigue. Gluconeogenesis is a metabolic pathway that results in the generation of glucose from certain non-carbohydrate carbon substrates by converting muscle protein and fats to glucose, and this occurs in the liver. Glycolysis is the process of converting glucose into energy, and the body has 2 types of reactions, one that build products such as muscle or glucose, or ones that break products down. When products are being built, energy is required, and when they are broken down, energy is created. So glycolysis is one process that breaks products down and therefore creates energy. Gluconeogenesis is the reverse of glycolysis, with an extra step, which means it is a process that requires energy that needs to be put into the reaction so it can occur. So firstly, pyruvate gets converted into phosphenolpyruvate. This is the step that requires a substrate in order for it to occur. When phosphenolpyruvate is converted into pyruvate in glycolysis, energy is released from this, and therefore it is exothermic. So doing the reverse is not energy favourable. So the sub-step makes it so that less energy needs to be used. And by adding carbon dioxide into the pyruvate forming oxaloacetate, by then removing the carbon dioxide, the energy is created to add the phosphate into the pyruvate to rearrange the double bond. And then after the product is formed, the steps are similar to glycolysis, but in reverse, and they're just rearranging the previous compound eventually so they can form the final product of glucose.